Hello and welcome to the astrO channel. Today's podcast, we are joined with Dr. Zatrimaylov, a postdoc and astrophysicist, physics working on space and time, general relativity, wormholes, etc. Hello, Dr. Zatrimaylov. How are you doing today?
Nice to meet
Nice
you.
to meet you.
I'm doing perfect today.
Could, could you please give us a brief introduction of yourself before we start?
Mm, I completed a PhD at School Normale Superiore di Pisa in 2021. The topic of my PhD thesis was dark matter. Now I'm holding the position of a visiting professor at the University of Bergamo and working on warp drives and wormholes.
Yes, thank you very much. So, in today's episode, we'll be talking about general relativity. And before we start, I would like to give a brief introduction or a bit recap on what general relativity is. So, general relativity is basically Albert Einstein's theory of gravity, where he describes how mass and energy can curve the fabric of space time. Because through general relativity, he had thought of the universe is a fabric of space and time, and different masses and objects, such as our planets, stars, can warp themselves on the fabric of space times, which curves it. Now, this fabric of space-time general relativity can predict phenomena such as black holes, neutron stars, planets, and gravitational waves, etc. Because once we see or if we observe that the fabric of space-time is being warped or curved so much or so densely, we can predict that, oh, maybe there's a neutron star there, or maybe there's a binary pulses or binary pairs. Anyways, let's get back to the questions. So my first question is, what is one aspect of general relativity that still fascinates researchers today? Because now general relativity recently has been used for pinpointing gravitational waves and the phenomena out there in the universe, which we use with advanced technology today. So, what type of new research can really intrigue us or scientists and physicists today?
Well, the two most fascinating recent results were the discovery of waves and even more so the observational discovery of black holes. Because while gravitational waves are more or less understood, black holes still remain highly mysterious objects. So,
Yes. Thank you very much for that interesting answer. And also, how does general relativity predict the existence of black holes and gravitational waves? Because I know that general relativity can predict gravitational waves, but how exactly? Like, what observations do we use? What type of tools do we use? And so forth.
well, while in Newtonian theory, gravity is just a force. In general relativity, it's a field. And
Yes.
so, as it's a field, it can exist without gravitational sources. So, without gravitational sources, it is possible to have a modes of gravitational field, just like with Maxwell's electromagnetic theory. So you can
Yes.
have you can have electromagnetic waves even in the absence of electric charges.
Yes. And have we had any hope in finding any other black hole other than the only one that we found a few years ago, that was in the middle of our galaxy? Are there any others that we have predicted or seen yet?
Well, right now it's mm, um, mm, mm, well, by default, it's assumed that at the center of nearly every galaxy there is a black hole. There are many candidates for black holes. These kinds of objects are called quasars. For instance, this is just
Yes. Yes, please continue.
Okay, so yes, as for black holes, general relativity predicts them through the so-called Schwarzschild solutions for spherical mass distributions, because once the spherical mass distribution gets really small, when the mass gets squeezed in really tight, then you get some then you get the phenomenon that is known as the event horizon at the boundary. It means that once something, even light, crosses the horizon, it cannot get out. That's the
Yes.
point.
And also, I've been watching a lot of videos about how what would happen if anyone would fall into a black hole because I'm really intrigued by it. And they said that these like what they've said when you enter the event horizon there'll be some time dilation, and when you enter the singularity there'll be infinite or finite gravity, but they said it's not confirmed because we don't know the properties of black holes yet. But in your personal perspective, what do you think might happen when we enter a black hole?
Well, uh, um, there is one interesting theory on the topic. It's called the complementarity principle of black holes. So the point is to resolve the contradiction um, between the idea that all that information vanishes irreversibly in the black hole, and the idea that no information can be destroyed. So the point is the following. So, imagine there is an astronaut falling into a black hole, and another one watching him from far away. So, from the point of view of a distant observer, so effectively the black hole is is covered by a heated membrane, and so when this guy falls in, once he comes in contact with the membrane, he evaporates. So you can and the same happens for every bit of information, so nothing is lost, everything goes out. But from the perspective of view of this guy, he just crosses the horizon and goes inward, and nothing happens to him. So it's so basically, because once he gets inside, he cannot send a message to the guy outside. And so contradictory stories can coexist when there is no information channel between them.
And about the information when it's being conserved in a black hole, like if you throw an apple into a black hole, they say that the information will never be lost, but at the same time, energy cannot be created or destroyed. But there's a paradox, the black hole, the information paradox that contradicts and says that if you do like throw an apple into a black hole, it doesn't disappear, it actually adds to the black hole's mass. Is that changing?
Yes, but it's mm, mm, but still you cannot retrieve information. So in some way, yes, the black hole's mass becomes larger. The its volume and its area become larger. So its entropy grows as well. Entropy is in some way the measure of information that's stored inside the system, but there is no way to get it out. Black holes
Yes.
are believed to evaporate over time through a phenomenon known as Hawking radiation. But
Yes.
the Hawking radiation has, in its spectrum, it carries no trace of the information inside the black hole, because there is the so-called no-hair theorem. So the only properties of the black hole that can be observable are mass, charge, and angular momentum. And so once it falls inside the black hole, there is no way to so there is no way to restore this information.
Yes. Well, thank you because I really enjoy the topic about black holes. So I really enjoy talking about it as well. So for our next question is how can general relativity apply to our real life? Like why should other audiences or viewers understand general relativity? How does it impact us on every single day life?
Well, first of all, there is GPS navigation and satellites and geolocation. So that's the most obvious use of it. But also for the perspectives of space travel, if we'd be planning to travel to faraway planets and systems, then we would obviously need to take into account general relativity, because with Newtonian mechanics we would just make mistakes on this scale.
But do you think general relativity can be used in the future to create maybe artificial intelligence or anything that could be more futuristic?
Well, that's what I'm working on right now. We're looking into the so-called warp drives. A
Oh,
warp drive, so like as you've said, in general relativity, space-time is curved by the presence of mass and energy. And so a warp drive is like a bubble, like a spherical region in space that moves us at a given speed, even including superluminal in principle. And then uh, and so you don't need energy to keep it going, and so you just place your spacecraft inside, and here it goes. Mm, but of course, there is no thing as free lunch in our universe, so if you want to create a warp bubble, you need negative energy density. That's one very big problem that we're looking
oh.
into.
Well, that's very interesting. I'm very happy to hear about your work, and I hope it'll be true in the future so we can all like go into space travel and explore any exoplanets or stars in the future. Anyways, so for my next question is, are there any observations or experiments that might change our understanding of general relativity? Because relativity did prove the elementary particles, which helped us lead to the idea of particle accelerators. But there's also an experiment done by an English astronomer after Albert Einstein published his work in 1915. His and the English astronomer had proven the general relativity by doing an experiment showing that light rays can be bent around massive objects. But is there any recent observations or experiments of general relativity that could contradict with the idea or prove it even more?
Well, there are two distinct phenomena in general relativity that are not present in Newtonian theory. Those are gravitational lensing, first of all. Because in Newtonian theory, as the light has no mass, it's not affected by gravity. But in general relativity, as it's a curvature of space-time, it also affects light rays. Judging by how the light from some faraway object is bent by the gravitational field of some intermediate object, then you can deduce the mass, the shape, and other characteristics of this object. The second
Yes.
phenomenon is gravitational waves, and we already have a, uh, a new field known as multi-messenger astronomy, when you compare the light signal and the gravitational wave signal from some objects. And this I believe that these kinds of phenomena would be instrumental to proving possible to studying possible deviations from general relativity and stuff like that.
Yes. Plus, it gave me a whole new perspective on general relativity. That's very interesting. Now, for my last question is for those who are interested in embarking on the journey of astrophysics or who want to pursue a career on it, what words of advice would you give them personally on your based on your personal experience?
Well, there are two distinct fields. One is theoretical general relativity, which I'm working on now, and the other is observational astrophysics. So I would say if you're planning to work in observational astrophysics, one very important thing is to learn data science because you would have to work with a lot of data. I would say
Yes.
it's uh, mm, after you've with when you have a physics background, say the astrophysics from a purely physical background, from a purely physical perspective, the these kinds of systems like stars and stellar systems and stuff like that, they're not that complicated, but you have to learn how to work with data. That's the point.
So, well, learning programming language or like coding is very important in astrophysics then.
Yes, in observational astrophysics, because just like in experimental particle physics, you have to work with collider data, so you have to learn how to analyze large data arrays and stuff like that.
And also, what is the most intriguing or most interesting part of astronomy or astrophysics that you find interesting or that you really like to work on or research about or really think about?
Well, if we're speaking about observational astrophysics, about something we can see with our own eyes, then again I would say black holes, because mm, it's the least understood phenomenon right now, and also dark matter and dark energy, but those have not been observed directly so far. For dark matter, we only have indirect evidence in the form of gravitational forces. So we see that the gravitational force is larger than it should be, and then from we can deduce that there is some unseen kind of matter. Yes, but this those have not been detected so far.
Yes, and I'm also very interested in black holes, but I'm also very interested in dark matter. I heard that you were also working on dark matter.
Well, I did my PhD in that
Oh,
field. So the idea that we developed was that at the center of some galaxies there could be some elongated string-like objects, and that could explain some of the observations. That's the point. So
right.
these kinds of objects, in principle, they could be made of dark matter, for instance, because there are also we know already of dark matter filaments on larger intergalactic scale. So smaller threads could be present at the scale of single galaxies. But also, there are some more speculative ideas like some grand unification theories. They predict the kinds of a kind of objects known as cosmic strings. So,
Yeah,
well,
yes.
and
Well,
it yes,
no, please continue.
and in these kinds of theories, it has been predicted that if they are formed, they would drift to the center of galaxies. So, who knows?
Yes.
I believe
Well,
that we have discovered something, but it remains to be seen what exactly it is.
Wow, that's very interesting. I'm really happy and glad that I was able to listen to your work on dark matter and wormholes and your research that's going on now. And thank you very much for sharing your advice and insights on astrophysics. It was really inspiring to hear based on your personal journey. And I'm sure that many young minds will be encouraged by your work. Well, thank you so much for joining the Astro channel, and I hope that we can soon talk again and learn more about your work and research and how it's ongoing. So thank you so much, and I hope to you join us again next time.
You're very
Thank you.
welcome. I would be happy.